To the seminar. So today's speaker is Dr. Dimitrije, who is currently the research associate at Institute of General and Physical Chemistry in Belgrade, Serbia, and who came to visit our group led by Dr. Tomislav Ivek. So he was born on 5th February in 1991 in Belgrade, Serbia, where he also finished elementary and secondary schooling. In 2014, he finished his bachelor studies of chemistry at Faculty of Chemistry, University of Belgrade, and in 2015, his master studies of chemistry at the same faculty. So he obtained his PhD thesis in 2020 at the Department of Chemistry, Ghent University in Belgium, with the topic luminescent lanthanide complexes for temperature sensing. He is author and co-author of 29 papers in Q1 and Q2 journals, cited 386 times and with H index 11. So his area of expertise are coordination chemistry, chemistry of lanthanides, molecular materials, chemistry of materials, nanomaterials, optical sensor spectroscopy, photophysics, and crystallography. And today he is going to talk about luminescent lanthanide molecular materials and their applications. So the floor is yours.
Good afternoon to everyone. Thank you for coming. Also, thank you for the invitation to come here and present some part of my research. So today I will talk about luminescent lanthanide molecular materials and their application. I divided in few areas, so introduction, then I will talk about lanthanide beta-ketone complexes, so those are small molecule materials, then lanthanide hydrogen bonded organic frameworks, that's one new materials, and at the end lanthanide metal organic frameworks, and I'll give you a broad conclusion. Why lanthanides are so interesting and unique? Because lanthanides are the first period of elements, so they have electrons in F or 4F orbitals, and that gives them unique properties such as photoluminescence or magnetic properties. Also, because with rising atomic number, the ionic radius is contracting because each one has one more electron in 4F orbitals. So of all these elements, lanthanum and lutetium are not emissive or do not have also magnetic properties. All the others have, except promethium, which is only one that is artificial one. All the rest can be found in nature. Also, because of their chemical properties, which is just the difference of one electron, they are difficult to extract, refine, and that's why we call them also rare earths, because they're difficult to process when they're extracted. The lanthanide luminescence comes from the Laporte rules, which gives allowed and partially forbidden and forbidden transition. And in lanthanides, it's forbidden from 4F to 4F orbit, which can be slightly relaxed when we introduce in the crystal field or Wigand field of these items. So in my case, when we work with molecular materials, we introduce in the Wigand field. We have terms, so we have ground term and emitted term, which are then split in the levels. And those sub-levels are influenced by the Wigand field. Here we can see the diagram. Also, what is interesting, they are emitting in whole broad range of electromagnetic spectroscopy from ultraviolet, visible, near-infrared up to the mid-infrared. And here, for example, we can see europium, and it's emitting in visible, in red, like here. Terbium emitting in green, samarium red, orangish, but in case of erbium, which emits in near-infrared at telecommunication optical at 1.5 microns, as an example. So how we can excite? We have three different mechanisms how we can excite. Downshift, so we use high energy photons like UV light, and then we have emission at lower temperatures. Or down conversion, when we can make, it's a two-photon process, when we can from one high energy level photon get two lower energy photons. This can happen in infrared, so you can use a system with ytterbium and praseodymium, and praseodymium can excite and then transfer electrons to ytterbium, and then can emit two photons. And at last, we have up conversion system, which is now quite popular in inorganic materials. So you can excite with low energy electrons, photons such as 980. You have ytterbium as an initiator, and then you use erbium or neodymium to emit at low energy, so you can emit in green or red part. Because they're partially forbidden, they have low Moore coefficient, so you need high energy to excite them for electrons. To overcome this, we can use antenna effect. So we can use organic dye, such as the ketonite, to absorb the light, and then that light is transferred to the nearby lanthanide, which will emit its unique emission. How on this Jablonski we can see, so we absorb in singlets, ground states to excited state, from where there are few ways how the electron can relax. One is radiatively, known as fluorescence, non-radiatively, or to go through the intersystem crossing to the triplet, slightly stable triplet state, from where the same electron has three ways to relax. One is radiatively, known as phosphorescence, non-radiatively, or at the end, to transfer its energy to nearby lanthanide, where the 4f electron are from ground state excited to the excited state, and then they can relax. At the same time, relaxing, non-radiatively, and then from here, the electrons can be 4f electrons can be relaxed radiatively, what is known as photoluminescence or non-radiative. Also, because lanthanides are small oscillators and forbidden, the high energy oscillators such as CH, OH, and NH group can influence on the quenching. So we have the lifetime that we measure, it's observed one, it's radiatively plus the sum of all non-radiative relaxation that can happen. So in case of near-infrared lanthanides, they can be easily quenched with CH-OH groups because of the second, third harmonic CH-OH groups. Here we can see that we have some different vibrational moving of stretching of CH groups, such as symmetric or asymmetric. With Spielberg law, we can calculate the radiative lifetime for the near-infrared, because the same levels that are used for the emission are also absorption levels. For the visible one, it's a little bit difficult because different levels are absorption levels and emission levels. And we have few ways. One is energy gap law, so that we can make a difference between energies, or second is photoradius energy transfer, where we have the distance between the donor and acceptor overlap, and of course radiative light. Application, we have wide range of applications that we can use lanthanides. We are using it currently in LEDs or phosphorescent lamps. So in lighting, lasers, neodymium YAG, ytterbium YAG lasers, telecommunication for optical fibers, displays, so in our phones everywhere. We can use it for bioimaging, light conversion, even for security for anti-counterfeiting, or sensors, different types of sensors such as temperature sensor, pressure sensors, and many other types of sensors that we want to make. For the temperature sensing, we know what is temperature, and we want to measure the temperature at different levels, and even in nano levels, so we need something small that can help us to measure. Currently, by this year, sorry, I don't have the new one, $6.86 billion is the market for the temperature sensors, because in every process we need to know to measure the temperature that we want to know. And there are three regions of temperature that are interested: cryogenic, physiological, and high temperature. There are wide range of how we can measure. Some are on the spectrum shift, so the movement of the emission with the temperature. lifetimes, then we can have, if we have a polarization, we can use polarization, bandwidth, so broadening, or intensity of one, single intensity of one level, or two. In the case what I'm going to show, I work mostly on the Hershey-Metric temperature sensor, which are on two different emitting levels. And there we also have two types. One can be on the single sector, so we can have only one ion, such as dysprosium, which can have two different populated excited states, and then from there emitting at different wavelengths. Or we can have two different lanthanide poles. Systems that I will show are terbium European, terbium samarium, where they are communicating because the distance is short between each other. Here are some thermometric parameters. This is Boltzmann equation, and second one is what sides used, where we have alpha is the difference between non-radiative and radiative punching. What are we interested to know? The sensitivity, how sensitive is our system. Then to know the uncertainty, how much we have the difference between each measurements. And at the end, repeatability, how many times we can use this same sensor for measuring the temperature and having a good temperature sensitivity after 4 or 5 cycles. Lanthanide beta-dechetonides. What are beta-dechetonides? Those are small, quite simple, where we have two oxygen keto groups one to another. And in the free form, they also have these keto-anol polymerizations, so they can go from keto groups to anol. And this here, carbon beta, hydrogens in this one are quite easily can be extracted because they have quite pK, and then we can have our complexes. What is interesting, we can synthesize different types and can make broad range of different types of structures, like here what we can see, or introducing the silica, so we can make silica nanoparticles, or introducing the polymers, or just having the complexes. In this case here we have a single complex with tris complex with water as a counter as a neutral ligand, or we can use some different type of ligands which can help us. In a case that I will show you here, I worked with a simple one. It's known as acetyl-isocyanate fluorinated, where I synthesized. What was interesting in this work was that we did at quite neutral pH 7, so around pK of the beta-deketonate in this case. And when we put 1:3 ratio for the lanthanides, small lanthanides, so because praseodymium and neodymium are larger ionic radius. So here we have beta-kiss complexes where a sodium is bridging, is a counter ion, but also bridging ion. And for the praseodymium and neodymium, we got tris complexes. When we increase the ratio between lanthanide and beta-deketonate 1:4, we also obtain the tetra-kiss complexes. And second one is with this phenyl rings, where we have a phenyl ring with beta-deketonate and phenyl ring with beta-deketonate, but we have in para position chlorine added. We wanted to see the difference, how this chlorine, which has negative resonance but positive induced level, how it will work on our sensitization. So, as an example of photoluminescence, here we can see European tetra-kiss complex in a solid state, and lifetime is around 850 microseconds. And when we introduce to the methanol, we reduce the quantum yield, but also lifetime, because we introduce more quantities. In this case, methanol, we have CHOH quantities, which can influence, while here we are in solid. And second one is what I was talking about last slide. So we have a phenyl ring and chlorine phenyl ring. We can see the increase in quantum yields by 5 times or even 6 times, and also increase in lifetime when we add also 3-phenyl oxide compound, which was here. You can see it's a phenyl neutral ligand, And we see increase in lifetime, but also increase in quantum yields, which is quite interesting. And this was interesting for me because this gave me opportunity to play with for sensors later on. Sorry, this is something not working. So first example is tetrapis complexes that I made by co-crystallization of europium and terbium in 1-to-1 ratios, where we have terbium peak at 545, which is a small one, and europium peak at 614. So what's happening, we have in this case going from not nicely, it should go from green to red. That is our interest. So that also not only by using the system like spectrometer or something, that, but also by our naked eye that we can see the change of the color for the same. And we have the relative sensitivity at 350 of 2.7% per Kelvin of change of the intensity. And the second example is terbium samarium. Here we were looking also 545 peak in green of terbium and 650 of samarium. In this case, this was at the time one of the first in physiological temperature range with samarium that we showed that it can be used. But this was good opportunity for us to see what we can go further. So the next slide, I will show you first terbium europium when we put it in polymetric acrylic here, but here we can see nice change of intensity of terbium at 545 and europium is more or less stable. What we want when we have ratiometric is that one is quantified by the temperature, and another one is more or less staying or getting a higher intensity. So here we can see nicely going from green yellowish to red color change. So when you see also by naked eye, you can see the change of temperature. And here we got at 313, almost 4.2% per Kelvin. So it's same 4.2% per Kelvin or 4.2% per degree. We can see the change of temperature, which is interesting. And it's just in a short period, temperature range from -20 to +80 degrees. But changing the ratios, we can play in a different temperature region. So it's not purpose can be changed just slightly adding or changing the concentrations or ratios of terbium and europium. Then I put it in silica and we got almost similar change of color and quite similar, it's same one. So we were putting same terbium europium. We were coating in this case of with the polymer silica coating on the top of silicon nanoparticles. We were putting coating of PMMA and 3.8% at 20 degrees. So it's quite good for the purpose that we want if we want to use it in cells or something like that. Now I will show you, so in this case, same terbium and samarium. Samarium is more or less the constant and terbium is dropping, which is quite interesting. Also, we have now changed from green to orange reddish, and we got it 3.64% at 313 kelvins, which is increase of almost 1.3% compared to the first generation of our temperature sensor based on terbium samarium, which is good. And we can even try to make it better. Same we did for silica coating. In same temperature region, here we were going from green to yellowish. It changed a little bit the color scheme, but we got quite good results. Here we can see that we have almost 0.4% just change of, in both cases, of percentage of in PMMA and silica coating that can be induced by the quantical filter because it's quite high oscillator for all the lanthanides. At the end, here we can see the temperature uncertainty, which is quite low, it's almost 0.02%, and repeatability of 3 cycles of 95%. So how we were doing this, we would heat up to the highest temperature, first cool it down, heat it up, measure once, then cool it down, heat it up again and again. But due to the setup constraints, we did only 3 cycles, not 4 or 5, because it takes a lot of time to heat up and cool. Similar was for the PMMA sample of terbium and samarium. And for the silica, it's quite good also. We're in the same region. Here a little bit higher, but that's because of the quantity maybe of the samarium, which we'll talk on the next one. Here, yeah, we can see the samples. So here are the per generation of the temperature sensors. We have 2.7, 2.3, here 4.1, but we go from 3.8 to 4.2. And here we go from 3.6 to 3.45 to 93. So just changing the ratios of lanthanides, we could see that we can enhance the sensitivity. Here we compare with some done already in solution, and we have quite a comparison done. For example, this is the bump, so we can somehow carry in quite larger. Okay, so for the quenching effect, this is most prominent and seen on erbium, near-infrared. So here an example, we can see erbium at 1.5 microns emission with 2 water coordinates, and when we introduce the 3-phenophosphinoxane, we can see intensity increase. But also we can see this on lifetimes. We can see that from 0.8 we go up to 7.5 microns, or 1.5 to 8, or for the samarium from 12 to 126. But only for terbium we can see just like 2 times, not 10 times more. Why? It's also, we calculate the intrinsic lifetime quantum yields, so lifetime and radiative lifetime. You can see also the increase significant. Why is this happening? Because we can see here on the crystal structure that we have the radius of CH and OH. What we found is that the closest CH contributes the most and closest OH group. Even if when we introduce the 3-phenophosphinoxide, which is quite bulky, and we introduce more CH groups, we reduce the OH group, but the concentration of CH group doesn't influence on the radiative lifetimes. So here we have how we did it. So we have overlap between donor and acceptor, which I'll show in the next slide. And the Foster radius is the crucial one. We calculate the quantum rates for the CH and OH groups, and also the efficiency of the quenching. And here I can show, so this is the tris complex, and this is water-free complex. Here we can see the first harmonic of water, second harmonic of CH, second harmonic of water, and third harmonic of CH. We can see that for erbium we have more overlap of second harmonic of CH and second harmonic of water. For samarium, which is orange, and neodymium red, we have second harmonic of water and third harmonic here of CH groups. And in blue is only shown the terbium, and you can see that we have only third harmonic of CH. That's why we see the different trend in terbium compared to the erbium, samarium, or neodymium. With the quenching, here we can see the efficiency of CH, which is less compared to the OH groups in neodymium, same as in samarium. OH is 99.99%. So what we would like in ideally is to have water-free complexes without any CH or OH groups, but that's quite difficult and quite expensive to obtain. Also here we can see closely how it looks the overlap of neodymium and samarium with a second third harmonic CH groups. And here we did a prediction of accuracy of our quantum yields, where we quite good obtained, except for the terbium, because there is existing a third harmonic of OH here, but it's quite broad and we cannot see it on diffuse surfactants when we measure it. So now I'll show you, so this was done on better ketone complexes or molecular complexes. Now I will talk about hydrogen bonding for hydrogen bonded organic rings. These premix are consisting of two moieties, so we need to have OH and NH donors, which then are bonded together. So we use an acid and some aromatic like urea or melanin as NH donors, and we can get these porous, quite interesting materials. In our case, we have melanin here, where we have CH and OH. So what's happening, we have hydrogen bonded from NH to OH here, and we can extend it. In this case, done by my colleague, we can see the excitation spectrum where we have a broad emission of this is a starting compound, and this is when it's hydrothermally treated to become the hydrogen bonded compound. And we can see the intensity of dropping of the ligand or linker in this case. And here we can see the emission absorption lines, Europe in this case. And this 393 is most intensive one. At the end, on the right, we can see on the B, we can see that we have emissions just of the European. And in this case here, we have a slightly phosphorescence of the linker, because what can happen is that we can transfer back small amount of energy from the European or lanthanide to the linker. Then here was done the doping concentration of the lanthanide, and at the end we found that the free one is the best concentration. And last time I showed the emission. Here we use the excitation or absorbance to calculate the thermometric properties. So this is also one way, another way how we can use these small lines. Unfortunately, due to the high absorption of the ligand and linker, we need to a little bit play with it, but we can see that two different levels in this case. Not the emitting levels, but accepting levels 7F0 and 7F1 are changing with the change of the temperature. And we got quite good sensitivity about 1.3, sorry, around 3-4 at 100 degree Kelvins, and then dropping down to 0.6. Forgot now by heart, but this is quite interesting. Another way how you can utilize the lanthanides for the thermometric properties. And last, I will talk about lanthanide metal organic frameworks or MOS. These are polymeric structures, coordination structures, which can have 1D level, 2D, or it can be 3D, so they can have pores. They are used already in gas separation, gas storage, CO2 capture, NO2, NOx capture, cavities, but recently in sensing. So you can use it with lanthanides in optical sensing. So we synthesize with this BTC, terbium europium pure, and in ratios here are shown the theoretical ones, different in hydrothermal. So we used a vial with our linker dissolved and lanthanide, put it in the oven, and got it. What was interesting is that these compounds crystallize in non-central symmetric, so we could see the second harmonic generation and multiphoton fluorescence. What is, you know a little bit better than me, because I did 1 year postdoc, so these are not third and fourth nonlinear range. Here we can see the crystals of terbium or europium, and we use this to track the crystallization with second harmonic generation. So here we see a rise of second harmonic signal, and then we have a constant, so we have a crystal that is floating because we have one dot that we are just concentrating, and then after some time it's dropping. Similar here we can see, and what we found that in half an hour the synthesis is done. So we showed a new way how we can track with synthesis the creation of the MOS. Similar we can see here, around the half an hour, we got the crystals, and after that, we saw some crystals floating in our laser, and we saw change of signal. PLs, what we saw here is this is 1 mole percent doped europium to terbium, so we excited in the ligand, and we got this emission nicely. You can see the peaks of terbium, europium. In this case, almost white light we got. We can use this also for temperature sensing. I didn't do it yet. And here we can see the lifetime of terbium, and here is pure terbium given just as a reference. You can see that they have more or less the same lifetime. And this is for pure europium. We can see that we have B exponential, so we have 2 different coordination sites that are influenced by lifetime. But in case when we are having 1 mole percent of europium in terbium, we got mono exponential, nice one of almost 1 millisecond. Why this is happening? Most probably that it has only 1 coordination site and it's around, terbium is around, so we don't see the difference in coordination site if it's on the surface or inside the system of the MOS. Okay, on next slide, we did a little bit spectroscopy. We can see nice, strong signal of second harmonic. Then, and also we did a multiphoton, but unfortunately, because we used terbium laser, which didn't have, we couldn't change the excitation level equivalent except 1054. So most probably, because this is around 300, we had 4 photons, not 2 or 3 photon excitation. So what we can see is the ligand excitation, because in this case here we don't see it, but with higher concentration we see a little bit around 450 a bump. So, and at the end we did also some microscopy where we used 900 nanometers wavelength as excitation, and you can see nicely second harmonic, multiphoton, and we can see that they are different when we overlay the images of second harmonic generation and multiphoton. And at the end, we can make with molecular materials versatile sparkles designed for lanthanide photophysical properties, which can be used for many applications from lighting to the sensors. We can tailor playing with the different ratios to design a temperature sensor in the different temperature regions of the interest which we can find. And at the end, we show that if we have non-center symmetry, we can have nonlinear optical properties, which can be used for the different exploitations, such as the quantum technologies. And at the end, I would like to acknowledge my co-promoters, Rick Van Doon, Professor Rick Van Doon, Christoph von Hecke, and Professor Anna Heckman from Ghent University, and members of Luminescent Lanthanide Lab and Extract, also Professor Flavia Artizio from Lumimo, Piedmont, and where I'm collaborating. She was postdoc at the time in Ghent together, and Professor Thierry Baptiste and Stefan Klovenberg from molecular imaging and photonics, where I did my postdoc, and also funding that gave me possibility to do my PhD, postdoc, current funding of ministry, my recently obtained project on temperature sensors for the young scientists in Serbia, and also I'm researcher at the Pathfinder project Quantum for Quantum Challenge Artemis grants. And thank you for your attention.
Are there any questions?
I have a question regarding graphs in the first part of your presentation. Yeah. So the color graph, what are the axes on it? Even before on the
just
when you talk about changing from green to red.
CIE graphs.
Yes.
CIE graphs, yeah.
So this year the graphs are what we had in wavelength.
Yeah.
And intensity change of the wavelength with the wavelength. So this is done in CIE calculator from Austrian. So you import your spectrum, so at 343.
Okay.
So you have an intensity and wavelength, so X is always in X, yeah, it's in that. X is wavelength, Y is intensity, and then it just calculates on the change of the, so the software does that. I didn't do it. So in the software, when you put the graph, it goes, so it in milliwatts per second.
It's a different way of representing
Yeah,
those
it's a different,
line
yeah, the line ones just
yeah.
to show you on the plot how to look nicer, better change, so that we can see. When you talk like here, you cannot see this one, it's green yellowish. We cannot see it. With this one, we just interpret it like this. What is interesting, we can use our cameras, which are CCD now, and if we make an app, we can track the temperature not with a spectrometer, just a UV lamp, and a CCD camera from our phone can show us the current temperature if we make a machine learning software or something, which I'm not capable of doing, but there are people who can do this. Yeah, so that's just a graphical, better representation how we can show the change of the color. Because here you cannot see this quite clear, the change from the green to.
Okay, thanks.
Yeah, okay. In case of the lanthanide based MOS,
Yeah.
so would you consider also as this as a sensor to some
Yes.
some molecules that would go into the
Yes.
smoke in
Where
and then influence the
yes.
electrons
So
from
yeah.
ligand to the
yeah. So in this case, because the pores are quite small, you can use it for, let's say, metal ion sensing. So for the heavy metals in water or something. So that's my idea in some future time when I have manpower in my own time to use as a sensors for metal ions. So you can, so some ions can go in, and what can happen if you had, let's say, lead, the intensity will drop of one of the two because there is some energy transfer happening from lanthanide maybe to the lead or from the lead.
Yeah, exactly.
So yeah, it would be the same principle what I want to use. So ratiometric, so to have two different ions, because two different centers, always one center will be, let's say, influence. If you have only one, you don't know what's happening. Of course, for the basic properties, you will work with one and another. So it's terbium and europium, and then the mixed one just to see which one will happen. There are some types you can have turn on. So when you add an analyte or whatever molecule that can enhance your emission, or you can have turn off. So when you introduce something, it's dropping your quenching. So there, you don't know. Unfortunately, it's a mystery still. So it's a basic science that nobody's doing. They're just making mocks and publishing. We want to talk how it's made and it's working and it's better. Nobody is doing the consistency and everything. So also like when I did this paper with the quenching, vibration quenching, they said, but that's a basic science nobody wants, but it's quite cited and people are interested in asking questions because it help us to understand better what is influencing the quenching. So yeah.
And you can design better MOS in
yes.
that way. Yeah.
Of course, you put, let's say, I said here theoretical. Yeah, that theoretical. So I used 1 mole%, 5 mole%, 10 mole%, but you don't know if it's 1, 5, 10. You need to do quantification with ICP, XRF or something to know what is real, because sometimes some ligands or linkers have preferential to the terbium compared to europium, but you can make it. Also, you can use it for lighting, for LEDs, for a lot of stuff.
Thank you.
More questions?
Yes. So if I understand this correctly, all you need is a source of quenching, and then So that would no, sorry, let me rephrase that. You need something that will change the way how your vibrational modes function, right?
Yes, or how the energy transfer will happen. If it's going to stop between the lanthanides because something else will, if you have a metal, maybe it will transfer from terbium to the metal, the analyte, let's say lead, not to the europium, because lead is has more energy. Match.
Yeah, this is fine.
So you need something. Also, when you do room temperature, you get one. But if we introduce temperature, cool it down or heat it up, we see the difference in the change of intensity of one of the lanthanides.
So what I'm thinking is there are people who do calculations that try to model influence of different external parameters to promote these vibrational modes and transfer of energy. So can you consider, so you obviously did consider chemical sensors, temperature sensors. How about mechanical sensors, something like that?
There are mechanical sensors also. So it's possible to make also pressure sensors, but not maybe with molecular materials because they're small and fragile, but with inorganic materials, there exists. So
no. My question was whether you feel these could be developed from MOFs, for instance.
For MOFs, not so much because they're quite fragile. Let's say they're just another derivative of a molecule, small molecules. So they're the complex, but made in a structures way, like this room. So pillars, you have a ligand, and that is a linker, that is this, and then on the joints, so you have on four sides, you have a lanthanide or metalite. And it can be also with normal metals for the catalysis or sieve storage. They use a lot, not like iron or other nickel or something. So yeah, they're quite versatile for some other, but in this case, they're not for pressure sensitivity, but also what is interesting, they are not influenced, the luminescence is property are not influenced by magnetic or the electric properties. So you can introduce an electric field and see it. With magnetic, you can see maybe the flipping of the intensity, like in polarization, but only this. So this is also something that can be used.
Thank you.
More questions? So nothing. So in that case, let's thank the speaker one more time. This is one speaker. Yes, I thought it.